In this video, we are going to talk about tangent planes and linear approximations. So in the video before this, we looked at partial derivatives, and we reviewed the meaning of a derivative. We said that in Calc BC or Calc 2, we use the derivative to find the slope of a tangent line or instantaneous rate of change. And so today, we're going to look at what does the derivative tell us when we have a 3D function or a function in 3 space. So starting with what we did before this class, so in Calculus 1 and 2. If we looked at the graph of a 2D differentiable function, when we zoomed in on the graph a lot, the graph began to look like its tangent line. So if we're looking at, something like this, so our y is equal to f of x. What I'm saying is if we choose a point and we zoom in on that point a lot, like a lot, then at that point, the graph begins to look like the tangent line. So what we can do is we can approximate the value of the function at that point using the tangent line. So what that's saying is at this point, or maybe the point right next to it, rather than actually finding the y value, we can find the tangent line and plug in x, which is often an easier computation, to approximate the y value at that point. Now, of course, in Calc 3, we're looking in 3 space with functions of 2 or more variables. So let's take a look at what we're going to be doing today. If we consider the graph of a 3D differentiable function, when we zoom in on the graph a lot, the graph begins to look like its tangent plane. And that should make sense. If we have a 3-dimensional graph, something that's 3D, when we zoom in, it's not going to look like a tangent line, it's going to look like a tangent plane. So of course this leads to the question, how do we find the equation of this tangent plane then? If we find two tangent lines, then the tangent plane is going to contain both of those lines. Okay, so if we look at this figure here, this blue is z, which is some function of x and y. And if we want to find the tangent plane at some point P, what we can do, and our tangent plane is this orange one, is we can find one tangent line and another tangent line going through that same point P. And our plane then, our orange plane, our tangent plane, will contain both of those lines. Okay, so the natural question is, how do we find these two tangent lines? Hopefully we recognize there are infinitely many of these tangent lines that are going to go through point P. So let's choose 2 that are convenient. We are going to choose the 2 lines that result when we intersect z is equal to f of xy with the planes y equals y naught and x equals x naught. So then, as you recall, the equation of a plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0, where x naught, y naught, and z naught is a point that's on that plane. Okay, so if we isolate then z minus z naught, what we're going to get is negative a over c times x minus x naught, subtract b over c times y minus y naught. Well, this and this, those are just 2 constants. So I'm going to call this constant little a, and I'm going to call this constant little b. So then what we get is z minus z naught is equal to a times x minus x naught plus b times y minus y naught. Okay, so that is just general form of a plane. So now what we're going to do is we're going to go back to these 2 tangent lines because we haven't used those yet. So now we are going to use our 2 tangent lines that result from the planes y equals y naught and x equals x naught. Okay, so the first one results in that line T1 that we see above, and that's when we intersect the plane y equals y naught with our function z. And so if we go back to this line right here, or that plane, and we plug in y equals y naught, we're going to get z minus z naught is equal to a times x minus x naught. Okay, so then the question is, what is this? What are we actually looking at? Well, this is a line in point slope form with a slope that's equal to a. A slope that's equal to a. Okay, so in this case, we're holding y constant, and our slope a then is going to be the rate at which z is changing as x changes. So I'm going to say that again. Because of this plane, we're holding y constant, so that slope a represents the rate at which z is changing as x changes. So what is that? That's the partial derivative with respect to x. So likewise, on the figure above, if we go to find the second tangent line, so that's intersecting with the plane x is equal to x naught. Using our equation of the plane above, we get z minus z naught then is equal to b times y minus y naught. So again, similar idea. This is a line with a slope of b. We're holding x constant. We're looking at how is z changing as y changes. So this is the partial derivative with respect to y. Okay then, so now, finally, where this leads us is we're going to go back to our equation of our line, or our plane, sorry, I keep saying line, the equation of our plane. We now know what A is, and we now know what B is. So, where this leads us, the equation of the tangent plane then is the following. Z subtract z naught is equal to the partial derivative of x at the point x dot y naught times x minus x naught plus the partial derivative with respect to y at the point x naught y naught times y minus y naught. So that is our equation of our plane. And again, thinking forward a little bit, what are we going to be doing with this? Ultimately, where we're going to be going is using this to approximate values of f or z. But before we do that, let's actually try an example. Okay, so at the top, I've written the equation of a plane, tangent plane again, just for ease of use. So let's look at example 1. Find an equation of the tangent plane to z equals 2x squared plus y squared at the point 1, 1, 3. Okay, so before we do that, let's do a quick little review of what this graph actually looks like. So this is an elliptic paraboloid. And as you can see from the equation of the tangent plane above, we're going to need the partial derivative with respect to x, which we get to be 4x. We're going to need the partial derivative with respect to y, which we get to be 2y. We're going to need to evaluate both of those at the point 1, 1. So we get 4, and then we get 2. Now, I didn't write the z value. We know the z value if we plug in x and y. Z is dependent on x and y. So I could have written 1, 1, 3, but I didn't. I don't need an equal sign there. So what that gives us then is z subtract 3 is equal to 4 times x minus 1, add 2 times y minus 1. If you want to leave your answer like that, that's perfectly great. A lot of times what we'll do is we'll just solve for z, which would give us 4x plus 2y subtract 3. So that's our equation of the tangent plane. Okay, and again, talking a little bit about why we're doing this, let's look at the figure below. So this kind of rainbow figure is our elliptic paraboloid. From y is -4 to 4, and x is -4 to 4. And this orange is the tangent plane. Now, when we zoom in, we notice this tangent plane is pretty similar to the curve, but when we zoom in even more, so we only look between 0 and 2 for x and y, our original curve, our z, is almost the same as the tangent plane. So again, where this is leading us is to approximating. So now that we know how to find the value of how to find the equation of a tangent plane, let's move on to actually using a linearization. In example 1, the linear function, so the tangent plane, 4x plus 2y minus 3 is a good approximation of f of xy when we have a point near 1, 1. Okay, and that's because this tangent plane that we found is the tangent plane at 1, 1. So for example, if I plug this point in to my linear approximation, so I take 4 times 1.1, add 2 times 0.95, and I subtract 3, what I'm going to get is 3.3. Now, if I actually find the value of f at that point, so this was 2 times x squared plus y squared, I get 3.3225. So this value on the right is the actual true value of z at that point. The value on the left, our 3.3, is an approximation. And what I want us to notice is that these are super close. Okay, so a little bit of vocab. L, so our tangent plane, is called the linearization of our function at the point 1, 1. The approximation itself is called the linear approximation, or the tangent plane approximation of f at the point 1, 1. So remember the equation of a tangent plane. So z minus z naught is equal to f of x at the point x naught, y naught, times x minus x naught, plus f of y at the point x naught, y naught, times y minus y naught. So that's the tangent plane, which tells us then the linearization, it's just rewriting the tangent plane. Generally, it's written as L, and that L is really just z. So all we're doing is taking the tangent plane equation and we're solving for z. Z naught is just f at the point AB plus f of x at the point AB times x minus a plus f of y at the point AB times y minus b. Okay, so all I did was change x naught, y naught to a and b, and I solved for z. So the linear approximation then tells us that the actual value of f at the point xy is about equal to the linear approximation. So all I'm doing is recopying above. Okay, so this is our actual value. This is called our linear approximation of this value. And our tangent plane is the linearization. But that only applies, of course, if our function is differentiable at the point. So your next logical question should be, how do I know if the function is differentiable at a specific point? And that's what we're going to look at next. Okay, at the top, definition. If we have z is some function of x and y, then f is differentiable at ab if delta z, so the change in z, can be expressed in this form. Now, of course, we're not going to use the definition. There's a much easier theorem we're going to use instead. If f of x and f of y exist near AB and are continuous at AB, then f is differentiable at AB. That's the idea. Not sure why we ended up with this little parenthesis here. You can erase that. And it's a similar idea for 3 or more variables. So finally, after all this talk, let's actually look let's do an example and see what this looks like. Example 2, show that f of xy is differentiable at 1, 0 and find its linearization. Then use it to approximate f of 1.1 comma negative 0.1. Okay, so first we need to show that our function is differentiable. So I'm going to just rewrite our function. It's x e to the xy. In order for that to be differentiable, both f of x and f of y need to exist and need to be continuous. near the point 1, 0. So if I take the derivative with respect to x, I'm going to have to do the product rule here. So I get e to the xy, add xy, e to the xy. And then if I take the derivative with respect to y, I'm going to get x squared e to the xy. Okay, and so what we notice about these, both are continuous at 1, 0 and exist near 1, 0. So they exist at 1, 0 and then on both sides of 1, 0 or all sides of 1, 0. So what that tells us then is that f of xy is differentiable. At 1, 0. So that was the first part of the question. Show that f is differentiable. Now we're going to find its linearization. So from the previous page, linearization is just rewriting of the tangent plane. So that's going to be f of 1, 0, add f of x at 1, 0 times x minus 1, add f of y at 1, 0 times y minus 0. Okay, so our L of xy then is 1 add. These two I already calculated for us. I got 1, and I got 1 again. So simplifying all of that, our L of xy is equal to x plus y. So this is called our linearization. And now we are using it to approximate. So that's called our linearization. Our linear approximation is when we approximate f of xy. So our x e to the xy, we approximate that with x plus y. So f of xy is approximately x plus y. Vocab-wise, this is called our linear approximation. You'll also hear it referred to as the tangent plane approximation. Okay, so what that tells us then is if I want to approximate f of 1.1 comma negative 0.1, that's about equal to 1.1, add negative 0.1, which is 1. So we're saying f of 1.1 comma negative 0.1 is about equal to 1. Now, of course, you might want to know what actually is the value of f of 1.1 comma negative 0.1. If you plugged it into our original function above, you would get 0.98542, and that's rounded. So we can see our approximation is pretty darn close. Okay, so that's the idea with approximations, and we're going to add on to that with something next called the differential. So the last idea of this set of notes is the total differential. And so you can see the objectives at the top. We're going to talk about what is the total differential, and then we're going to use it to approximate a change. So we're going to start by looking out in 2 space. So we know in 2 space, dy is equal to f prime times dx. And so we have this figure right here that we're going to take a look at. Okay, so in the figure, you see we have some function in terms of x, and then we have a tangent line at that point, and we have the equation of the tangent line. So there's 2 things I need us to look at. This first one is if we have our x value of a, and then we add on a little bit to the next point. This difference right here horizontally is the change in x. But then we have 2 different changes in y. This delta y is the actual change in y. It's the actual change in y. So it goes from this y value to this y value. So we're going to write that down. Delta y is the actual change in y from x equals a to x equals a add delta x. dy, on the other hand, is the change in y using the tangent line. So it goes from this point to this point right here. So dy is the change in y when using the tangent line. So often we want to know delta y, but dy is much easier to calculate. So when our change in x is really small, so when this delta x is really small, dy can be used to approximate delta y. So we can approximate this delta y using dy. Now, of course, what we care about is 3 space. So it's going to be a similar idea in 3 space, except instead of using a tangent line, we're going to be using a tangent plane. And so this leads us to what is called the total differential. So the total differential, dz, is equal to f of x dx, f of y dy, or this is another way to write it. dx and dy are independent variables, or x and y are independent variables. So dx and dy can be any numbers. So x and y are independent variables, so dx and dy can be any numbers. So dz in this case would be the estimated or the approximated change in z. So dz is going to be the approximate or the estimated change in z using our tangent plane, which is where these then come from. We're going to take a small change in x. So then this dx, this change in x, we can approximate with x minus a. Okay, so we're going to take a look at just a base example, and then we are going to use this idea in some word problems. Consider z is equal to xy squared. First, we're going to find the total differential. So in this case, our z is a function of x and y, which is equal to xy squared. So we're going to need to find the first partial with respect to x, which is y squared. And then we're going to need the first partial with respect to y, which is 2xy. So then, using the idea above, this one for our total differential, we get dz is equal to y squared dx, add 2xy dy. So that's our total differential. Now we are going to approximate the change in z from 0.5, 1.0 to 0.503, 1.004. Okay, so using that change, or using that approximation above, here's what we're going to talk about. This dx and dy, change in x, change in y. So then our y squared and our 2xy, we take the initial value. So now let's use that differential to approximate the change. For our y, we get 1 squared. For our change in x, we go to 0.503, but we started at 0.5. So then we get 2xy. Again, we ended at 1.004, but we started at 1. So our dz is equal to 0.007. And again, this is the approximated change when we move from the first point to the second point. So then, of course, we might want to know, how does that compare to the actual change? So notation-wise, the actual change is delta z, and that's going to be the function evaluated at the ending point. Subtract the function evaluated at the initial point. So using our function above, that would be 0.503 times 1.004 squared. Subtract 0.5 multiplied by 1 squared. So our not dz, our delta z, our actual change, is about 0.007032, so on and so forth. So that is the actual change. And you'll notice our approximation is really, really darn close. Okay, so now that we know the total differential, what we're going to do is we are going to take a look at 2 word problems to end these notes. So let's take a look at example 4. The base radius and height of a right circular cone are 10 centimeters and 25 centimeters, with a possible error in measurement of as much as 0.1 centimeters in each. Use differentials to estimate the maximum error in the calculated volume of the cone. So of course, we're going to need to start with a function. We're told that we are looking at volume of a cone, so hopefully you remember the formula for volume of a cone. It's 1/3 pi r squared h. So we're going to need the partial with respect to r, and then we're going to need the partial with respect to h. So the partial with respect to r is going to be 2/3 pi rh. Our partial with respect to h is going to be 1/3 pi r squared. So then our total differential is going to be 2/3 pi rh dr, add 1/3 pi r squared dh. And next thing we are told that the possible error is as much as 0.1 centimeters in each. So what that means is the error in r is at most 0.1, and its absolute value, because it could be bigger or smaller, not bigger or smaller, it could be negative or positive. And then same thing with h. So where that leads us to then is dv is equal to 2/3 pi, radius of 10, height of 25, times 0.1, plus 1/3 pi times 10 squared times 0.1. So our dv then is 20 pi, or approximately 60/3 centimeters cubed. So the question is, what does this mean? This means we may over or underestimate the volume by as much as 63 centimeters cubed. That is the maximum error in over or underestimating, or maximum error in calculating the volume. Okay, so we have one last example, this example 5. At this point, if you're comfortable, I would suggest pausing the video and trying example 5 on your own. If you're not comfortable yet, or you're just not feeling that, then stick with me through the last example. The dimensions of a rectangular box are 75, 60, and 40 centimeters. Each measurement is correct to within 0.2 centimeters. Use differentials to estimate the largest possible error when the volume of the box is calculated. Okay, volume of a box, length times width times height. So I'm going to call these x, y, and z. So this one has 3 variables. So I'm going to need the partial with respect to x, and then I'm going to need the partial with respect to y, and then I'm going to need the partial with respect to z. So then our differential gives us yz dx, xz dy, and xy dz. So then substituting in the values we were given, we have 60, 40.2, 75, 40.2, and then 75 multiplied by 60 times 0.2. So our dv, our estimate in the error, our estimate in the error is 1980 cubic centimeters. So of course you might ask, how big is that actual error? Well, let's just add on to this a little bit. So fun fact, if you were asked to calculate the volume of the box, you would say that's 75 multiplied by 60 multiplied by 40, which is 180,000 cubic centimeters. So then our error is 1980 over that 180,000. And of course, remember that 1980 is just an approximation, which is about 1.1%. So it's pretty good. An error of 1.1%, not bad at all. So I know this was a long one. Thank you for sticking with me. For our next video, we're going to talk about chain rule. So if you have any questions, please make sure you write them down and bring them to class. See you next time.